A couple announcements. So homework 2, your second go at homework is posted. It's due on Friday. I think normally I'll post it on Friday night or maybe Saturday morning, something like that. So it was posted. It's in the same spot. Go to the files on Canvas and it's there. This particular homework is covering resistance and thermal generation. So you'll be looking at an application where you're modeling like the temperature profile on a battery as you start to run the battery, what happens internally, and kind of what's the limits to the dimensions of the battery. So you'll combine in the same problem the thermal resistance and thermal generation. Homework 1 was due last Friday, a couple days ago. I think most everyone didn't have a problem submitting it, so if you did have an issue, let me know. Hopefully there's no problems there. I think the solution was posted this morning. It should have been, so you can go look at the solution. Normally what will happen is I write up the solution. As the TA is grading, they may have further clarification to the posted solution, and so there might be an edit to it or something like that. But my first draft of the solution is available to you. While it's still fresh in your mind, just go back and look at that. In terms of grades for that, we'll see how it goes this semester, but my expectation is that the graders will return the grades to me within about a week to 10 days after the assignment. They have a lot to get through, right? 132 of you to get through, so I give them at least a week to do that. But you should see your grade posted to Canvas, and then you should get some specific feedback. So you'll get, if there's a point deduction, you should get some specific feedback for why that was and maybe how it was different from the solution. Yeah, so look for that next week. I guess any questions or anything on the homework or anything else on homework 1? So you may have noticed that the homeworks are a significant effort, right? So I want you to maybe anticipate that. I don't want it to take like 10 hours to get through, but it should be take enough time. It's a real problem. You have to kind of think through it. Okay, question? Do you have any update on the extra TA office hours? Thank you. I don't have an update, but I'll make a note. I'll make a note and follow up with them. Any other questions? Yeah, so anticipate that the homework will take a little bit of time. I don't want it to, like I said, take forever, but I want you to have an experience of like what I think are real problems. Obviously, I'm not an expert in every area, but spent enough time working on real problems that I can kind of share that with you. So they are supposed to feel like real things you'd have to do kind of in a small container because you're still in just a course and it's one course of many that you're probably taking, but set aside time to go through it carefully. You'll also see that this theme of sketching recurs, and so like it or not, I think that's a really good way to develop intuition and understanding of what's happening. So we'll try to keep practicing that and developing skill and anticipating what things are going to look like. Okay. All right. Let's look back and kind of picked up. We had a few slides from last time that I want to finish up. So remember last time we're talking about resistances. We left talking about radiation resistance, and we, using the radiation rate equation, came up with a resistance that sort of looks like this, right? What's at the top here? So we have a driving potential, which is TH minus TC, and then you have this resistance, which also includes TH minus TC. So there's a couple of things to maybe say about this. So when you're solving problems like this, the first thing you're going to do, if you have to compute a resistance and you don't yet know what the temperatures are, you have to start by guessing one or more temperatures. So let's say, in this case, we don't know what TH is in this problem. So let's say we're going to guess a value for unknown temperatures. in this case TH. 2, compute the resistance. 3, solve the problem, or solve for, let's say, Q dot. And then 4, go back and update TH. Right, so it's an iterative process. So you want to start by guessing, solve your problem, use that information to then compute a new actual value of TH, and go back. So in ease, that sort of looks like you assign a guess, solve the problem, set up the system of equations, and then later go back and comment out your initial guess, uncomment that new expression that solves directly for TH, right? So hopefully that sort of makes sense. I think you'll maybe go through examples of this, but it's an iterative process, yeah.
So is that like a situation where we don't know TH and we do know Q dot?
Yeah, so like you have to still have like one unknown for every equation, right? They have to line up. But you'd let's say know Q dot, not know TH, solve for TH, and then go back and compute TH again, right? So I'm not saying that especially clearly, but yeah, that's the idea. Yep. It doesn't get you away from having to have one equation and one unknown for each. Okay, so the other thing to say about this is there's another way that you can write this. So instead of having to write all this out, there's another more approximate way of writing it. So we can write our radiation is approximately equal to, so we take sigma, let's write it this way, 1 over sigma epsilon AS. That's all the same. The approximation is to say, if we took TH and TC, and we take the average temperature of those two, the average temperature and then the product of those terms together is actually close to 4 times T bar cubed. So we'd say this is all times 4 T bar cubed, where T bar is equal to TH plus TC over 2. So if you can get close on, say, knowing what the temperatures are going to be, you can actually compute this resistance and get kind of a handle on the problem. So we'll write the approximate way as in the bottom. The one on the top is the exact. So that'll give you the actual radiation resistance. So then the error between these two methods, you can actually plot it out. I did this at one point, and so here's the chart. Let me just kind of show you what you're looking at here. So this is showing, zoom in. So this is showing the error between these two methods. So one is this 4 T bar cubed. The other one is computing it the exact way. So perfect agreement is right here, right? So 0 error. And what you're looking at is on this axis, the cold temperature, and on this axis, the hot. So let's say you have an emitting surface that's at 700, and you have an absorbing surface that's at 300. Right, that tells you that the error is right here, right? So it's about 15%. So you'd misestimate your resistance by about 15%. Okay. So the rule of thumb is the closer the temperatures are together, the better this approximation is. If you're looking at something like, molten iron or something down to room temperature or cryogenic temperatures, it's not a very accurate approximation. So just be aware of that. Okay, questions on anything on resistance for radiation? Okay, there's a couple other resistances I want to talk about. So contact resistance and fouling resistance. So these resistances are a little different, but they sort of act in the same way. They're an impedance to heat flow. They prevent heat from flowing as freely as it otherwise would have. So just quickly going through these, contact resistance occurs when you have like two materials that are in contact with each other, and you have conduction from A to B, but those materials are imperfectly contacting each other. But if you take like a microscope and zoom way in, you're going to see that actually it's not like a nice smooth surface contacting. There's these little bumps and ridges, and so there's actually like air gaps or some sort of a break in the conduction from material A to B. So that introduces impedance to heat flow, right? That heat flow has to funnel through this small area or maybe be radiated or convected. And so that resistance looks like kind of a infinitely small temperature drop when you plot it out. And so it looks sort of like this. So let's say we have two materials, material A and then material B, right? And they have maybe slightly different conductivities. Those are supposed to be straight lines. So if you introduce a contact resistance right at this boundary here, at this boundary X, it would look sort of like this. So you'd have this occurring, then you have this immediate drop, and then you have this other drop occurring, right? So it's this like infinitely thin drop. It's like a vertical line that you draw. But again, the idea is you have this temperature drop from one side of this surface to the other side. And it impedes heat flow. So the same idea applies for fouling resistance. You have this maybe layer of film that builds up on a solid, and then it impedes heat transfer due to convection. It looks very much the same as contact resistance, but it's for fluid flow to a solid as opposed to two solids. Okay, so then you need the actual formula for these, right? You need to evaluate them in some way. So contact resistance is normally like this. We say RC, which is our contact resistance, is some coefficient R double prime C divided by the surface area AS. Right, the surface area is this area that's in contact. So the units on R double prime C are usually K meters squared per watt. So you would be given or have to look up what R double prime C is for your application. If you've got like plastic to metal or metal that's clamped or just whatever the system might be, you'd have to look that up or you'd have to test it yourself. For this class, you'll be given those coefficients. Same thing goes for fouling. RF, or F down here, fouling resistance is R double prime F divided by AS. Again, AS is the surface in contact with the fluid. Same units. One thing I want to point out is people always will take that R double prime C or R double prime F and think, okay, it's per unit area, so I better multiply by area. Right, don't do that, that's wrong. In this case, because it's a specific resistance, the meter squared goes in the numerator, and then we have to divide by area to get it back out. Right? So it's related to area, but just be a little bit careful with the units on that. Questions on this? Yep.
What was the AS in the contact resistance equation?
Well, question was, what was the AS in contact resistance? It's just like the area that's in contact with the material. So you have a block here, you have a block here, they're touching each other. It's the area that's touching. Yep.
Would it actually be only the area that's physically touching, like the gap area, or do you assume it's just the whole?
You assume the question is it only the physically touching area? So you assume it's the entire profile, right? It's the entire block. And the reason why you do that is because that contact resistance is supposed to account for all the bits. Like it's supposed to account for the fact that not everything is touching. So if you have just a small fraction that's actually in contact, that coefficient is different. And so actually what you see is like there's these tables, like I said, and you can look up, okay, it's steel to steel, and they'll have like clamping pressure. So for these different values of clamping pressure, that coefficient will change. So it is a measure of how much is in contact. Yeah. Okay. Yeah.
Would fouling resistance kind of be like sweat?
I'm not sure I understand.
Like sweating, like if you're like a human body?
Oh, so yeah, that's an interesting. So is fouling resistance sort of like the human, like a layer of sweat or something like that? I guess it sort of is. I mean, it's basically like physically what's happening is you have like, let's say a pipe. In that pipe, you have steam running through it. Well, steam is almost never pure, and so over time it'll just build up junk, right? Like a layer of maybe some oxidized thing. And that layer has a different conductivity than the base metal does. you need to account for the fact that there's additional resistance associated with that layer that's built up. For humans, it's a little bit more like complicated because you're evaporating, and then so you're looking at the conduction across that, say, water layer, and then you have this evaporation, which is really a very good heat transfer mechanism. So it's a little bit different, but it's the idea that you build up a layer and there's an impedance with that. Okay? Okay, so that takes care of thermal resistances. Let's talk about lecture 4 now, which is thermal generation. All right, so I will recap our thermal resistance discussion. I won't talk about the last 3 since we just did that. But remember, we can represent thermal resistance with this like conceptual model, and we're always thinking about heat flow, a potential, and an impedance. That impedance is something like a constriction in area or poor conductivity or something like that. So we can represent conduction in these different coordinate systems: Cartesian, cylindrical, spherical. And that resistance is just a measure of how hard it is to get heat from one part of the coordinate system to another part. Convection is related to Newton's law of cooling, and then we just talked about the other ones. Remember, there's series versus parallel. So any resistances that are in series, you just add straight up. Any resistances that are in parallel, you have to add the inverse and then take the inverse of that sum. Combine them together by adding them. Right? So that's just the general idea for resistance. It's a really powerful concept.